Okay, we are live and we are going to be studying, well, digital circuit and design. So let's get right into it. Again, this is not going to be like a normal stream where I usually try to teach. This is just me actually understanding what I'm going to teach and how I'm going to teach it. So it's a different one, you know. Let's see. I'm going to start off with LUT. Lookup tables. Again, I think all of the stuff before this, I'm gonna do it at a later date, you know, make a video about all of these, because stuff like, what is it? This binary, I think we already went through the basics of binary, but we couldn't complete it. I think, yeah, this is where we left off, but at the gates and stuff. I'm gonna upload, you know, probably a streamer video about that soon if again there's enough demand. But right now we're gonna, well, do this the stuff after my mids because, well, that's what we have to do. There's just some tips that I'm, you know, putting up because, well, they're in my notes, and if they're in my notes, that means they're probably important. I made them. I don't know. I think it's been a while since I made them. As the states, the LUT lookup tables are extremely, what would you call it? Oh, I'm sorry, I did not mean to do that. I think I have to like stop myself from accidentally minimizing that. But anyways, lookup tables, there you usually make, you know, circuits through logic gates and AND gates and NOR gates, but not lookup tables. Lookup tables, well, it's sort of like what it states in the name. Imagine you have a Word file and it has all of your answers and all of your so-called questions. So whenever a user asks a question, it goes into it goes into your notes, checks what question, you know, what type of question you asked, and what is its corresponding answer, and then it gives you the answer. So I think it's used for highly optimized stuff and for certain applications. You do the truth table first for two input and gate. Combination is what you do. The actor said like for once. Okay, okay. So let's do one thing. It's also input. Yes. Don't worry, just paste it. This is my, what you might call it. I think you can see them. Okay, yeah, this is much better. So these are my notes. We can probably, you know, look at these and see what's going on. The example that I have used is your two example, two lookup table example. Let's see what this reads. So, your two-lot example, you drew the truth table for a standard 2 input and Y gate. Yes, I did. It's referring to this. So you drew the truth table for standard 2 input and gate Y dot AC. Okay, I don't think it. Oh, oh no, it's talking about this one. Okay, okay. It's talking about this one. So yes, the outputs for the combination are 0, 0, 1, 0, and 0, 1, 1. Yep. Below that, we drew how a LUT table implements it. I'm just going to call it LUT. The values 0001 are stored in a small memory cells labeled latches in your notes. Okay, okay. So these are latches. This is, but you might call it memory cells. Okay, okay. These memory cells are fed into a 4-to-1 multiplexer. Mux, your inputs A and B acts as the select signals. If A is equal to 1, 1, then mux selects fourth memory cell. Okay, that's pretty simple. Okay, okay. I understand that. You're probably going to be going through, let's say, a lot of complex stuff in here. If you really don't understand it, well, first, I guess you could state that when you don't understand it, or you could write it in the comment section, and if there's, again, enough demand, I'll probably make a more detailed explanation on all this. Expanding to a 3-LUT input table. Yes, okay. Now we're moving on to a 3-input one. Bottom of the first page, you start exploring a 3-input. Yes, A, B plus C, that's the basic, what would you call it, the equation. Because there are 3 inputs, 8 possible combinations from the truth table. On the second page, you drew a high block. Oh, I should also get the second page, yes. I should get the second page, which is right here. Oh, I accidentally started Minecraft. I do not know why I did that. God damn it. Now I have to close that up. Ooh, okay, there you go. Yes, yes, yes. Come on, just do it. Just do it. Okay, don't ask much. It's the same thing, but now there are 8 inputs and 3 inputs and 8 latches, we can call them. What it states, because there are 3 inputs, 8 possible combinations. On the second page, you drew the high-level block diagram. I also need to kind of differentiate what's the difference between a high-level block diagram and a low-level block diagram. I don't quite remember. You know what? Let's look at that. First of all, I think we should just simplify that. Finish this instead of 4 1 plus 3 8 to 1 blocks obviously because 8 to 1 when I put 8 inputs 8 inputs. I don't know if it's 8 inputs, I guess it's 8 inputs to handle 4 8 possible truth table outcomes. The 4 inputs A, B, and C are select lines for this larger box. Okay. The difference. Block diagrams show the overall system architecture, major components, and their interactions, focusing on the big picture level, on the internal logics, algorithms, and component level implementations, acting as a detailed blueprint for developers. Okay, okay. So, from what I understand, high level is overall overview of the entire system. whilst, let me just, this just allows for me to infinitely scroll sideways whilst, well, low level is the more intricate stuff, like gates, components, etc. For instance, this block diagram would include stuff like, oh, wait, how the hell did that happen? I don't know how to do that. Oh, goddamn, I don't know how to do that. Oh, that's fun. That's fun. That's fun. So it could include stuff like this. For instance, this is a DAC. This is a, what you call it, a PWM. This is a digital to analog converter. Yeah, a digital to analog converter. And this is a wave modulator. And the entirety of this we could call, what would I call it? A beat machine. So this would, be how a high-level diagram is, but I guess a low-level diagram, uh, block diagram. Wait, yeah, wait, hold up. Let me just check out examples. You gotta say that you love me. The story will tell. God, I don't know what's the example of a low level. Example. I might be mixing them up. You know what? Let's scratch this. Or wait, let me just explain the difference. Let's try this. And by the way, I'm also like simultaneously, well, not simultaneously, but I'm also watching One Piece. I'm literally like right at the start. I'm watching the lockdown arc, and it's literally it start, but mm, it's the lockdown arc where like Luffy sort of is about to deal with what's his name, Daddy something, but like I watch it really slow whenever I'm doing work. I just like to have it on the other computer, so it's something just like there. High level diagrams to show the overall system architecture, major models, how to use the system of system that. At the end of the night, we don't have to worry ourselves. At the end of the story, in the meantime, I'm sorry not to worry now. No, it's not the same, I'm sure. Oh, it's not to leave you, but I'm sure. Low diagrams, blueprints. Okay, the low level diagrams are like low key blueprints. Exactly how it works under the hood. It exposes the precise logic, timing, and internal wires to write both code troubleshoot a specific component using use. So it's the current monitor. Daily flip flop, percent comparison. No, that's what's happening. You know what? Let's do one thing. We will. I guess we will watch till we'll study till about 9 o'clock. Let's see how far we go. After that, let's do a watch party of One Piece. God fucking damn it. Okay. Yeah, I'm not getting any visual examples here, but I think this is the best we're gonna do. I'm gonna search on this a bit later. The exact thing. Okay, so what it's this is all telling us is that we can then take show the inside workings of each box. That's how that moves. I think now we should move on to what we're actually doing. At the bottom of the second page, you notice two very practical points. NSP and FPG is most is highly accurate. Lastly, let's just do, I guess, one small point, which is also in the notes. Since we are doing FPGAs, what we most likely use is 4 and 6. Oh, 4 and 6 watt. Oh, you see, yeah, that's that. That's all that I have on this lecture. I think we should probably move on towards our next lecture. How should we write it down? I guess number 2. Next lecture. Or maybe I should hold on, let me number 2. Next lecture. Yeah, that's better, I think. Can we get more color? I kind of want to try another color. Let's see. How about this? I think I kind of like that, but it's too dark. Yeah, it's too dark. That's perfect. You know, just give me a minute. Okay. On my other computer, like Windows is giving me an update too. Well, it's giving me a notification to update. I really don't want to update though. Okay, let's move on. Let me just get the next lecture. Do we even have a next lecture? I don't think so. I do. I don't think so. I do. Maybe I didn't. I think I do. No, I don't. No, I do not. And this is not DSD to do. This is not DSD. This is DSD. Let me get this loaded up. Don't need to worry when the sun at the end of the story. If you're the time, don't need to worry and enjoy. I know it's hard to say, but I wish you would. No, seem to leaving arms to feel. Let's put that in. I say that you're sorry, and I need to worry myself. At the end of the story. And is you okay? Is you okay? And is you okay? Have you all actually watched the Michael Jackson movie? Like, I don't know. I've heard a lot about it, but I've also want to watch it. I have watched Project Hail Mary though. You know, kind of like that. Okay. We got our next notes, and let's bring them over. They're about finite state machines. Yes, so don't worry, just based it. Finite state machines. I have another one. Let's just put them both here. Copy image. Yes. Don't worry about it. Can I crop? Yes, I'm gonna crop that. Oh god, then this is gonna take a whole lot. No, forget it. Let's just rotate it. What's 19? And there you go. So, let's see what these now talk about. So LUTs use combination logic, which is obviously where only the current inputs matter. FSMs, or are finite state machines, which we're not now going to discuss. They a column no, they don't. Sorry, sequential logic. Oh God, I'm hating this writing. Okay, what's next? So let's look at state diagrams. How we visualize these finite state machines. This is like how we do state I output value, input value into itself, etc. etc. We'll go into it in probably more detail. Oh, I just remember what we could do. No, that's for later. For instance, for ease, I could probably do something like this. And I'm just making things harder for myself, I'm not. Probably am. Probably am. Now it's the abstract arrows and circles and arrows into actual additional hardware. If it's made of three distinct physical pairs, okay. This is for this part. The block of logic gates looks at the inputs and the current state to calculate what the next state is. The state register flip-flops the actual memory when the positive clock hits these flip-flops, capture the next state and turn it into the present state Output combination logic with a block of gates that uses the present state and sometimes the inputs to determine the final output of the whole circuit. Okay, okay. Next we move on to a parity checker. I don't know what a parity checker is. Okay, it's just a check, I guess. But not an even checker. Even the state is equal to 0 starter if the input is 0, the number of ones hasn't changed. So, the number of ones hasn't changed, so you loop back to the even state. If the input is 1 and the count becomes odd, so you transition to the odd state. If the input is 0, then it's the odd state. Compensating again. Okay, we just simply set the two states. We'll get the diagram structured into a table prepared for hardware logic. Convert our knowledge into a table, such as this. And then drive the Boolean logic, you know, how it actually goes. I do have, I think I did make like a sort of what you might call it, a simplified bubble, an arrow diagram, which is in the notes, which is in the picture. At the very bottom of the page, drive the actual digital media version of the circuit. Based on the table, this means to physically put your parity checker. Wait, no, just. Need to do is a single XOR gate, exclusive OR gate for the next state logic, and an even. The one present state. The flip-flops are obviously used to hold memory. That's why we needed to hold the present state. What I have in mind for this. And that is the end of this lesson. Well, the lesson not happening now. Maybe it's FSM is linked somewhere else, I guess. see that it is here. Okay. My first day full. Here we're talking about more machines, but before that, I can see other stuff. Where the hell did I keep my stainless steel? DSD. Worry less than feelings. Pretty sure that's the end. Okay, I think that's it. Before moving forward, I would like to see if there are any more stuff that I need to discuss on this. Oh my god. I hate this. So notebook, I'm trying to use Notebook LM because there are a lot of stuff. It's just not. Mm. Let's add sources. Okay, let's add sources. Copy text. And story. You gotta say that sorry, you hold me down. It's nothing to worry. You know what? Let's do one thing. I just realized I really need to lock in for, well, a college course of mine. So we're gonna be doing like a sort of mega, what you might call it, a mega stream for signals and systems. But when should we do that? I want to do it for next Thursday. Yeah, that's it. That's it. Next Thursday, I'll do a, well, I'll, let's say, I don't know, 6 hour stream about signals and systems. Let's see where that goes. But I think I'm gonna have to unfortunately cut this short again. I'm not sure. Let's just say let's take a break on this because I got some things to attend to. Maybe watch some One Piece. Okay, so going forward, I think we'll do more machines, which is sort of like what you might call it, a extension of finite state machines. Let's write that. And there was one other type of machine I forgot. A Molly machine, I believe. Well, let's see when we get to that. Right now, I think. Oh, that's it.